Howdy, folks. So, today we're going to start the chapter about reactions, reaction types, and reactions that occur in aqueous setting. So, it's a shortest chapter, more focused on reactions in general, but we'll go ahead and get started. Now, the first thing we'll talk about is the idea of a balanced chemical reaction. Now, if you've had any chemistry in the past before this is probably the one thing you're most familiar with. The idea that how to balance a chemical reaction. A chemical reaction is, of course, the conversion of a reactant into a product. The reactants are just, whether they be element or compound, they are the ones that will have a rearrangement of atoms. There'll be bonds breaking, and in the product stage we will have bonds forming. In this reaction, you'll see four atoms of iron undergoes reaction with 3 oxygen molecules to form 2 iron 3 oxide ore molecules. Note that the 4 atoms of iron match the 4 atoms of iron on the right. The 6 atoms of oxygen match the 6 atoms of oxygen on the right. So the arrow shows that the reaction proceeds to the right. We can draw these guys in any way, whether we have an arrow going down and draw the iron oxide below, or we could write this in reverse with the arrow going left to the iron oxide. Technically, many reactions can go both ways. That if you apply heat, which you do in a blast furnace, you can turn iron oxide back into iron. How can you tell a reaction is taking place? There are many different ways. Some include changes in color, production of light, so if it's just glows or generates light, formation of a solid, so if you started with no solids and suddenly you have a solid, formation of gases, usually a good hint, and absorption or release of heat are often good hints that a reaction is taking place. Not all of them have to have occurred. And some of them can be somewhat false positives, as, for example, I would not call dissolving a solid into water a reaction, but that can absorb or release heat. When you mix a solid with water to form a hydrate, it can change color, so I wouldn't necessarily guarantee that it is a reaction. But note how several hints include the state or the phase of matter, whether it be solid, liquid, or gas. And don't forget, we will often use the phase aqueous as well. This is the focus of this chapter. Aqueous meaning a solution dissolved in water. Now, in describing a chemical reaction, we want a balanced chemical reaction. We want everything to be the same on both sides of the reaction arrow. The same number of atoms of each element need to be on both sides. We are not allowed to change the subscripts in the given chemical compounds. The product that is formed is defined by the subscripts. If we change the subscripts, we are changing the product. It may be easier to balance that iron compound, if it's FeO instead of Fe2O3. But FeO is iron 2. Fe2O3 is iron 3. Different products, so we cannot change the subscripts. So the only way we can do is change what we call the coefficient, which is the quantity of the given compound that is formed. Now, a coefficient should almost always be an integer value. We want the lowest integer values for our balanced chemical equation. But there is only one exception to this integer rule, and that is not going to come up in this chapter. But in a special definition called enthalpy of formation is the only time we will use non-integer values. So we look at the chemical reaction. This is the thermite reaction. If I throw aluminum and react it with iron 3 oxide, we form iron solid and aluminum oxide. If we count the atoms of each type, we have 1 aluminum on the left, 2 on the right. 2 irons on the left, 1 on the right. 3 oxygens on the left, 3 oxygens on the right. The oxygens are balanced, but the metals are not. So all I have to do is double up the aluminums on the left and the irons on the right, and suddenly we are in sync, in parity. And so once they're balanced, that is a good chemical equation. Now, a good chemical equation should tell us a lot of things. It should be able to identify the products and reactants, their reaction proportions, so it's balanced, their physical states, so how do they look, and even the potential, while we will not always do these, the heat, the enthalpy, the energy produced or consumed, maybe whether light is produced or consumed, whether a catalyst is needed. So some of those things can be included in certain equations to fully flesh out what is going on. That I should be able to look at the equation and figure out what is going on. So there is what is needed. Now, we have these 3 practice equations. So, how do we balance them? I'm going to take them one at a time. They're not hard. I will purposely leave out the states of matter because they are not going to be useful right now. Then Al2SO4, magnesium, and magnesium sulfate and aluminum. So, with that in mind, let's go ahead and look at these. This one, copper, that's good. Oxygen 2, oxygen 1, not so good. So how do we balance that? I am not allowed to make this 1/2. I'm not allowed to split this up in any way. So I have to double this. However, we always need to recheck. 2 copper, 1 copper, so I need to double that. Once I've doubled that, 2 copper, 2 oxygen. 2 copper, 2 oxygen. This 2 applies to both elements. Don't forget that. A lot of people seem to forget that, and it's pretty impressive how it screws things up if you do not remember that. So, okay. So the key thing here is take it one step at a time. One step at a time. When you modify something, go and see how it may have changed your results. 1 carbon, 1 carbon. 4 hydrogens, 2 hydrogens. 1, 3 oxygens. 1, 2, 3 oxygens. Okay. 1 carbon, 1 carbon. We'll leave that there. That's fine. Now, whenever you have oxygen in multiple locations, like in 2 different compounds, always solve oxygen last, if possible. However, if solving oxygen changes something else, we want to change that too. So with that in mind, I'm going to go, okay, there's 4 hydrogens, 2 hydrogens. I need to double that up. Now 4 hydrogens. 2 plus 2 is 4. Crap. I am not allowed to. There's an odd number of hydrogens here, odd number of hydrogens on the left, even number on the right. And I'm not allowed to put a fraction. Well, here's something you can do. You are allowed to temporarily put a fraction down. However, we cannot keep this. This is 1. If I do anything here, it throws off these numbers. So I am only allowed to put a fraction here right now. So 1 plus 2 is 3. 2 plus 2 is 4. So I need 1 more oxygen. So to make 1 oxygen, I'm going to make this 1 1/2, or 3/2. Now this is not correct as written. It is balanced, yes, but is not the best way. So how do I make this balanced? Well, I need to get rid of all fractions in here. To get rid of all fractions, I'm going to multiply both sides by the factor of 2. So this is 1 over 1, or sorry, 2 over 2. That's 2 over 2, that's 4 over 2. So when I do that, it gets 2 CH4O, which is methanol. 3 oxygens goes to 2 carbon dioxides and 4 waters. Now it is balanced and there is no fractions. When we are dealing with this, so aluminum sulfate and magnesium goes to magnesium sulfate and aluminum. You can absolutely treat all of the atoms individually. Balance the sulfurs, balance the oxygens. However, it is easier to leave the sulfate as one unit. As we would have learned in Lewis structures, that sulfate looks like this, and if it's going from one state to another, from here to here, it is not changing. And if it's not changing, we can just leave it as 3 sulfates. 3 sulfates, okay. There's 2 aluminums. Well, that's easy enough to fix. 2 aluminums. 3 sulfates. Easiest way to fix that is putting a 3 there. Now, because 3 applies to the magnesium and the sulfate, I need to put a 3 there. Now, everything is balanced. 2 aluminums, 2 aluminums. 3 sulfates, 3 sulfates. 3 magnesiums, 3 magnesiums. Treat that as one unit, and it'll make your life a lot easier when it comes to balancing that. As I said, you can absolutely break it apart, but it's easier this way. Now, we're also going to classify chemical reactions in this chapter. One, there's going to be recognized patterns of rearrangement and driving forces as the 2 major ways of classifying this. The patterns of rearrangement is what I'm going to talk about in this video, but over the next couple videos I'm going to talk about the driving forces. And I guess I'll talk about the driving forces a little bit, but the idea here is that we can classify reactions into one or more category based on how the atoms rearrange. Combination, decomposition, single replacement, double replacement, or combustion. These combustions, all these patterns are seen throughout the majority of our chemical reactions. And if we can recognize that, we can kind of tell what's going on. Then we can further discuss the driving forces behind them, whether they be acid-base, precipitation or oxidation and reduction driving forces. So the basic reaction types are these. The combination is simply as one expects. Two elements are combining to form one new compound. Two elements, or they could be two compounds. I've given an example of each. Both of these technically classify as combination. Zinc oxide plus carbon dioxide forms zinc carbonate, also known as zincite or smithsonite. Notice that two things have now bound together into one big compound. But uniquely, sodium can react with chlorine gas to form sodium chloride salt. Very violently, by the way. It doesn't matter that there's two sodium atoms for every one chlorine, or that there's two sodium chloride salts. The idea is that two individual things, two individual reactants are coming to form one reactant type. Well, combination is to combine together, decomposition is to break apart. So when two or more break apart, we form AB goes to a compound, breaks apart to form two. So one thing decomposes, breaks apart to form two unique ones. Hydrogen peroxide decomposes to form water and oxygen. That's why hydrogen peroxide will go bad over time. It will naturally decompose. We put in a little trace of stabilizer into the hydrogen peroxide to delay this effect, but it will undergo this decomposition. Potassium chlorate will decompose under heat to form potassium chloride salt and oxygen gas. That is something that will happen. Now, single replacement. That reaction is the key reaction in Death of a Gummy Bear. Google that. View that video. It is a great demonstration of you catalyze this decomposition by adding sugar. Single replacement. When we're saying replacement, we are swapping out one pair. A single replacement means we're swapping out one element within a pair. This is the key thing for this. This one is a element and a compound react and they swap places. So in this case, aluminum swaps places with iron, or you could have hydrogen swaps places with zinc. It doesn't really matter what's swapping, as you have an element and a compound coming together and swapping places. Double replacement. Double replacement is when we have a double swap. Two different elements are swapping with each other in the forms of the compounds are rearranging. It's no longer just pure elements, and now it's compound A and compound B completely swap around. It is the equivalent of the do-si-do, swing your partners round and round, and you're swapping partners. Your HCl is swapping the H with the silver, so we form nitric acid and silver chloride. HCl and sodium hydroxide are swapping with the H and the OH are swapping with the Na and the Cl, and we're forming sodium chloride and water. We'll talk more about this in a minute. And combustion is just simply a specialized form of it. It can be a combination, but it's also a type of. It's not quite a single replacement. You couldn't even call it a double displacement. It's a very specialized type of combination. where oxygen is combining together with objects to form binary oxide products. The most common one is oxygen reacting with a hydrocarbon. Every combustion with a hydrocarbon produces CO2 and H2O, water and carbon dioxide. You burn any hydrocarbon and that's what's going to happen. However, combustion can occur with other things such as sulfur or in nitrogen. Various other things can undergo combustion, but the most common one is our hydrocarbons. Now, you'll notice some of these reactions have asterisks by them. That is because they all experience one of the three driving forces, which I'll be on the next slide. There are three driving forces: precipitation, acid-base, and redox. Redox stands for oxidation reduction reaction. It is an electron transfer reaction that someone loses electrons, someone gains electrons. In sodium and chlorine, sodium loses electrons, chlorine gains. In hydrogen peroxide, oxygen is losing and gaining. And potassium chlorate, chlorine is, oxygen is losing electrons, chlorine is gaining electrons. Aluminum is losing electrons, iron is gaining electrons. Hydrogen is gaining electrons, zinc is losing electrons. And in the combustion, oxygen is gaining electrons, and carbon and hydrogen are, I think carbon's typically losing the electrons. But then in the double replacement situation, the first reaction would be a precipitation, which we'll talk about in a minute, and the second one is an acid-base, which we'll talk about later as well. But the driving forces, this is what we're going to talk about in the next video. These driving forces, what is going to make a reaction occur. All reactions have an energy input to start. They're all in essentially a little valley, a little miniature valley. It's a ball that's in a little divot. It's not moving. However, with a little bit of force, you roll it out of that divot, and then, depending on where you're at, you're either rolling it uphill a lot or uphill a little, and then once it reaches the peak, it's going to roll down to the low energy spot. Driving forces are the energy that pushes us to a more stable state, a lower spot, just like rainwater is going to flow to the lowest point on the ground. Well, reactions are going to flow to the lowest energy spot in a reaction diagram. Now, some of these things are going to be energy-based, some of it's going to be randomness-based, entropy, mixing, but driving forces are going to be what's pushing these reactions to completion. And these driving forces that we're going to talk about are precipitation reactions, acid-base neutralizations, and redox reactions, or oxidation reduction. A precipitation reaction is one where you have a double displacement where a solid precipitate, a solid crystallizes out of two aqueous solutions. The atoms of one element combine with the atoms of another element, and they slowly accumulate, they nucleate and tumble out of solution. And we'll talk more about why that is later. And a neutralization reaction, which is our acid base. An acid, which is considered a proton donor, an H+ donor. And a base, which is our proton acceptor, our hydroxide. will combine together to make from two ionic bonds to a covalent bond that forms water. Once we're in that covalent bond, it's a lot harder to break that covalent bond than it is to break an ionic bond. And of course, the byproduct is almost always a salt. Salt is just, remember, an ionic metal-nonmetal mixture. An oxidation reduction reaction, or redox, electrons are transferred. Remember how we talked about that atoms will want to lose electrons to become like a noble gas and gain electrons to become like a noble gas? Well, this is with a little bit of energy, you're going to pull off these electrons and give them to someone who can better use them. You're like, I'm taking the money from here and I'm investing in there so that everyone can win. And that's kind of what's going on there. But so electrons get transferred, so the resulting byproduct has a net stabilization energy. But that is as far as we're going to get on this video. Thank you for your time.